All right, welcome back. I thought it might be easier if we actually use an example to teach the rest of the 95 to 99.7 rule, okay? So we've got this lot of example here. I've kind of cut out the rest of the examples that were in the slideshow just so I could actually focus on drawing the diagrams and understand what the rules mean. So we've got a box of biscuits and it's the statistics itself have been normally distributed. So on average, the box is about 252.5 grams, and the next score from that would be, either 1.7 grams up, so about 254.2, or it could be, 1.7 less, so 252.5 take away 1.7. Okay, and then that way we can start spreading out evenly the standard deviations from the mean. So if we're going to focus on doing the 68 rule, when we talk about the 68 rule, it just means your graph, okay, center point being the mean, which is 252.5, means one standard deviation to the left, which would be about here, and one standard deviation to the right, says that if all these amount of weight is approximately 68% of the biscuit boxes. So around 68% sits between this range to this range. Question is, how do we find this in this range? So to find one standard deviation less than 252, all I got to do is 0.5, sorry, take away one standard deviation value. And that gives me, yes, I am using a calculator for that, 250.8. So technically speaking, this range would start from 250.8. Okay, so that's the lowest of the 68% majority of the boxes. Start from 250.8 grams. Then the higher part of my 68%, so the max, and choose a different color now, here is going to be, rather than subtract, you are actually going ahead. Therefore, you are adding 1.7 equals 254.2. So all of that information just told me that my range of 68% of my values starts at 250.8 and it ends at 254.2. Now the remainder of the results, which is the 16% here, and the amount 16% here to make my beautiful bell-shaped curve, says that anything less than 250.8 is about 16% of all of those biscuits that were in the data, and everything over 254.2 is the remainder of the 16%. And how do we know that? Because that's what the 68 rule says. And if we add 16%, 16%, that's 100% of all my data. And it's spread out equally, and that's how we've distributed it. Now, how is this going to help me? Well, if the question asked you how much percent is from 250.8 to 254.2, you could say directly it's 68%. I just want to show the slide questions that were on it, and I don't know where I've put them. Not there. This. No, change of plans. We're going to go back to the first question. All right, so if I had to say what's like 68% of those biscuits, like what's their weight, I could say, well, they start from 250.8 grams to 54.2 grams, okay? I'm gonna, oh, that's not what I want. I'm gonna show you how to do the rest of the bell-shaped curves, but using the different rules, and how, like, the further I go, the range would become a lot more as well. So let's do the next graph I want to do is the 95 rule one. Okay, so my shape still looks the same. Oops. Yep. It would look something like this. Okay. But this time around, what's it saying is, and again on page 347 says 95% of the data lies within 2 standard deviations of the mean. So remember previously it was 1 standard deviation, now the value is from 2 lots of the standard deviation. So what's 2 lots of 1 standard deviation? What's our standard deviation to start with? 1.7? Did I find that? I just thought it becomes a bit simpler if we just work out what are 2 lots of our standard deviation, which it happens to be 3.4. Okay, so that means from the mean, which was 252.5, 2 lots, so 3.4 to the left is going to give me my lowest range of my 95%. Really need to get used to writing better. So you take away 3.4 is, let's just say here, 249.1. Oh dear. Okay. And now we add the value of 3.4 to the mean, and that gives me 255.9. Okay, so that means all of this, when I add 2 standard deviations to the right and I take away when I add 2 standard deviations to the right and when I subtract 2 standard deviations, I get 95% of the data. Okay, remainder from 95 to 100 is 5%, which means this part here is the leftover 2.5%, and this part here is the leftover 2.5%. Okay, so a question could easily ask me, what's 95% of the weights? And my answer would be 95% of the weights actually start from 249.1 all the way to 250.9. Okay, I can't write the rest of it. It's cutting off. But here it's meant to end with a 9. Oh, it worked. Okay, and the third theory that says 99.6, let's do that in a different color. Let's go rainbow. All right, 99.7. It means, again, your data is normally distributed, but you're actually finding where does the majority of 99.7 sit. So again, your mean is 252.5. The textbook definition says that for us to draw 99.7% of the data, it lies within the 3 standard deviations. So 3 lots of your standard deviation value. So 3 times standard deviation was 1.7. And let's find that value, which is 5.1. Sorry, that's only 5.1. Okay, so that means you started from the mean, you added 3 lots of your standard deviation this way, and you get 252.5 plus 5.1, and you get, let's just say this is how much your jump was, your 3 standard deviations. as 257.6, and 3 lots of standard deviations subtracted from 252.5, take away 5.1 is 247.4. So that means from here and to here, this is 99.7% of your biscuits. So the minimum of around 99.7 of your biscuits, they start from 247.4. That's meant to be equal. And it ends around 257.6. But the remainder of 0.3%, which are here, 0.15, half of 3, will either be less than that amount or it would be higher than that amount. So 99% of the biscuit boxes sit in this range here. And lucky last, which is the most easiest one of all, and it's not even actually stated in the rule itself, is the 50% one. It's pretty obvious as it suggests. So if your mean is 252.5, 50% of that will be less than that amount, and 50% on the right-hand side will be more than that. And I forgot to draw my normally distributed data, so I might just finish that off like this. You know, that's where it sits. That was meant to be green. Yeah, I hope that has helped a little bit. Thank you.